This conference will now be recorded.
So, very good evening. Today we are starting a new chapter, that is mechanical properties of solid. So today we will be learning about mechanical property mostly. Hello, madam. Is everything all right? Is okay. I think it is audible, isn't it?
Yes,
Okay.
yes.
So today, yeah, today we'll be learning what is elastic property, plastic property of solids, and we'll learn about stress, strain, etc. So mainly the elastic property of a solid we'll be discussing today. So let me tell you what is elastic and plastic property first, then I'll write the definitions of those. See, by rigid and solid body, we mean generally a solid hard object, hard solid object, and solid rigid object has a definite shape and size. Okay, so that has definite shape and size. So this is the property of rigid and solid body. Solid, rigid, solid object. Okay. So rigid doesn't mean that it is too hard to make any changes in the shape and size. In reality, if we apply certain force to solid objects, they can undergo changes in the shape and size. They can undergo change in the shape and size. And the force we apply to change the shape and size is called the deforming force. So we can say in a single word that solid objects can be deformed by application of external force. And the force which is required to deform a solid object is called deforming force. So a force which changes the shape and size of a body is called deforming force. So we need a force to change the shape and size, that is called deforming force. All right. So what is elasticity then? See, if suppose an object changes its shape and size upon application of the force. So suppose an object changes its shape and or size upon application application of deforming force. Okay, what happens if the deforming force is removed? Force is removed. See, there are certain objects. There are certain objects which gets permanently deformed in shape and size even after removal of this deforming force. They cannot regain their original shape and size, or even they don't have the tendency to regain their shape and size. And some objects are there, they tend to regain their original shape and size after removal of the deforming force. So those objects which regains their original shape and size after removal of deforming force are called elastic object. So we'll write the elastic and elasticity. Elastic objects and elasticity. So if a body regains its original shape and size, after the removal of deforming force, then it is said to be an elastic object, and its property by virtue of which by virtue of which it regains its original shape or size, or sometimes both, is called elasticity. Okay, I'll give you certain examples. Suppose you take a rubber band. Okay. Now you apply certain force and deform it. Before it tears out, if you leave, then you look, the rubber band will regain its original shape and size. So rubber band is one of the example of elastic objects, and its property is called elasticity. Now there is another type of objects which I had already explained, that some objects will not regain their original shape and size. Those are called plastic, and their property is called plasticity. I'll write down the definitions here. Okay, let me write here plastic and plasticity. Plastic and plasticity. So the definition will be exactly opposite. If a body if a body does not regain its original shape and size, original shape and size, even after the removal of even after the removal of the deforming force, force or forces, okay, then that object then that object is called plastic, and their property their property is called plasticity. Okay, so I'll give you an example. Like if you take some plastic plastic object and then deform them, take any plastic, thin plastic, okay, and then deform it. See, you'll not look that the plastic is regaining its original shape and size. It is exactly opposite to the rubber. Okay, so we have learned what is elastic and elasticity, what is plastic and plasticity. Now there are two more terms related to this plastic and plasticity and elasticity. There is something called perfectly elastic body, and there is something called perfectly plastic body. If a body regains its original shape and size immediately and completely after the removal of deforming force, then that kind of objects are called perfectly elastic objects. That means perfectly elastic objects will regain their shape and size completely. original shape and size completely. But in general, in reality, elastic objects will not regain their exactly original shape and size. They tend to tend to regain their shape and size, but they may not get back the original shape and size. So that is the example of this perfectly elastic body is quartz fiber. So now I am just discussing about perfectly elastic and perfectly plastic. So I'll give you certain examples. I am just not writing all the definitions. Perfectly elastic. What does it mean? It means that an object regains an elastic object which regains the original shape and size completely. That is called perfectly elastic body. Example is quartz fiber. Quartz fiber. Okay. In many experiments we use quartz fiber. Now perfectly plastic body, it is exactly opposite to perfectly elastic body. So perfectly plastic body will not at all regain its original shape and size after removal of the deforming forces. Okay. So those are called perfectly plastic body. I'll give you an example, that is chewing gum. See, when you just extend it and then leave it, you see the shape and size. Once shape and size of chewing gum is changed, it never regains its original shape and size. So chewing gum is one of the example of perfectly plastic body, or there are many other examples like putty, then paraffin wax, paraffin wax, paraffin wax, paraffin wax. These are some examples of perfectly plastic body. Okay, so we have got to know so far what is elastic body, what is plastic body, and there are something called perfectly plastic body, perfectly elastic body. Okay, so perfectly elastic body will regain their shape and size completely after immediately after the removal of the deforming forces. Now, in reality, there is no existence of perfect. There is nothing called perfect, sorry, perfect perfectly plastic or elastic body. Actually, these plastic and elastic properties are actually mutually exclusive. Suppose you have an object which is very good plastic, then that will not be a like an elastic object. Okay, So nobody is perfectly elastic or perfectly plastic. All bodies found in nature lie between two extreme limit, like maximum that are perfectly plastic and perfectly elastic. These are the limits of extremum. So any object you see in this world, in this universe, any object you see in this universe lie in between this limit. Okay, what are those? So perfectly elastic. This is one extreme, and another extreme is perfectly plastic. So in reality, objects will lie in this mid region. So these are neither perfectly plastic nor perfectly elastic. If some object has more plasticity, then it has less elasticity. If some object gains more plasticity, then it more elasticity, then it will not have it will have less plasticity, kind of that. Okay. So now we'll go and learn about interatomic forces, and in terms of spring ball model, we'll try to discuss how we can understand about the elastic and plastic properties. Okay. See, in this universe, whatever solid we see, whatever solid you take, they have atoms, and like atoms, and atoms actually upon bonding them forms molecules, and that's how many molecules comes together and form a solid object. So in the solid object, in a single word we can say that there are atoms which are connected to each other. Okay. So atoms in a solid are held together. Okay, held together, and in a compact space. That's why solids are having greater density in maximum cases. Some cases may be less density even compared to liquid. So mainly atoms are connected by interatomic forces. So they are held together by interatomic forces. And when these atoms will make a molecule, then the forces between intermolecular forces. So these are the binding forces of the atoms together in a solid. So interatomic forces or intermolecular forces. Now we'll see these interatomic forces which are which are responsible for binding all the atoms holding together in a compact space to make a solid. That interatomic forces actually varies. Suppose I have atom here and here. The interatomic forces actually it changes its nature depending on the interatomic separation. We denote the interatomic separation, suppose interatomic separation by small r. Okay, and see, we know they will be having electromagnetic interactions, so there will be some kind of potential energy, and also there will be forces also. In this case, since they are bound together, so this will be actually, the force will be conservative in nature. We'll see whether the force is, yeah. So we'll see this thing, that they have a potential energy. As we know, potential energy depends on the configuration. Configuration means depending on the shape, size. So shape, size again depends on this molecular forces, how or interatomic forces, how strong the forces are. If the interatomic forces is too strong, then object will not be very big. They will be compact. They will be situating or holding all the atoms together in a very tiny space. Anyway, let us see, depending on the interatomic separation, the nature of the interatomic forces when the nature of the interatomic potential changes, and we will represent the changes of interatomic potential and interatomic forces by this type of graph. Okay, so look in the so this upper one is actually interatomic forces, and look, this is the interatomic separation, this way interatomic separation, and this is the interatomic force as you can see in the vertical axis. And in the lower graph, if I name this as A, this as B, the B graph B is actually giving you the interatomic potential energy, variation of interatomic potential energy in terms of the interatomic separation. Now look this potential curve first. So this potential curve has a minima. Suppose at a particular this this happens, it has minimum value at particular interatomic separation, that is R0. Okay, and look this minimum potential energy position, and exactly at that position the interatomic forces becomes zero. Interatomic forces become zero. So this R is equal to R0. This is called equilibrium separation. Equilibrium equilibrium separation, because at this separation forces between interatomic forces, I am writing IF, interatomic forces 0. IF means interatomic forces 0. This is called equilibrium separation. Okay, and the potential at equilibrium is the minimum potential energy state. So any system wishes to be in the minimum potential energy because that is the equilibrium states. Okay, now look this graph again. So if you look this R is equal to R0, R is equal to R0, the potential energy is 0. Now you this within this limit, see if this R is less or greater R0, like R, the interatomic separation is greater than R0 or less than R0, on the either side the nature of the forces are changing. You look, when we go below or less than R0, look, this is R0. Okay, this is R0. When you go less than R0 this way, look, the sign of the force which was negative earlier becomes positive. That means it becomes repulsive force. And also the potential also, you look below this R0, the potential energy also becomes positive. Potential energy also changes its signs to negative to positive. So this is repulsive force represent unbound states. So this is repulsive. So this position, which is R less than R0, is actually having repulsive forces, or this is called, so this is repulsive forces. Okay, and if you go R greater than R0, this side, see both the potential and the potential energy as well as the interatomic forces becomes negative, and it becomes minimum at some certain point. Okay, and then again approaches to 0. So this is how it varies. Okay, so the separation R0 is called normal or equilibrium separation. When the separation reduces below R0, the potential energy increases steeply. As you see, potential energy increases steeply below R0, and hence so potential energy increases sharply and interatomic forces becomes repulsive. Okay, and when it is R greater than R0, at that condition, interatomic forces are negative as well as the potential energy also negative. So negative energy states are actually bound state. Negative energy, negative force states are bound state. So in this, within this region, actually the system will be bound state. Otherwise, it will be unbound state. Okay. All right. So I hope we have understood this, that the atoms are held together by interatomic forces, and its nature changes by interatomic separations. If you go away from, like away from each other, then the forces between them becomes that becomes repulsive force. If you're if you go below R0, then this becomes repulsive, and greater than R0 will give you attractive. This is attractive force. Okay. All right. Now see what happens when a compressive force, or see, as we have seen that there are interatomic forces between, so there are maybe many atoms held together, so they have interatomic forces. If one of the force, interatomic force, is disturbed by the application of external force, then all others will have to experience the reaction and action of that changes in the interatomic forces. We'll see the spring ball model. So by analogy, we'll be able to understand how some object regains its original shape and size. So the atoms in solid may be regarded as mass points or small balls connected in three-dimensional space through springs. The springs represents the interatomic forces, as you can see in the figure, that the atoms in the solid can be regarded as small balls, and these balls are actually connected in three dimensions. Look, three dimensions means, see, this is one direction, this is one direction, this is another direction. So all of them in the solid, all of them are connected to its to its neighbors in three dimension. That means you are connected along x-axis, y-axis, z-axis. So this is three-dimensional structure you can see from here, right? So these are the spring, right? These are the spring, and this is the ball. Ball has a small mass. Now see what I am trying to tell you, that when we apply certain force, suppose along this way or along this way, okay? What happens when there is a force applied along this direction? So then this spring will be deformed. This shape and size of the spring will be deformed, and the effect of, since these springs are connected, this is very easy to understand. In our reality also we can do this. See, since this spring is connected to all others directly or indirectly, so all of them will experience the effect of this disturbance of one of the spring which is connected directly or indirectly to all the atoms in this structure. Okay, so this is strong spring ball model. So if we apply certain force, see one spring will be actually getting deformed, so there will be a force. Okay, so there will be see if I apply force over here, so this is action suppose, so the reaction will happen in all other springs. Normally balls occupy position of minimum potential energy or zero interatomic forces. When any ball is displaced from its equilibrium position, the various springs connected to it exerts a resultant force on this ball. This force tends to bring all the balls to equilibrium position. This explains the elastic behavior of solid in terms of microscopic nature. So if we go to the microscopic nature, we see kind of this, that interatomic forces, these springs actually represent the interatomic forces, and these balls, this is spring ball model, the balls represent the atoms, and when we apply certain force, one of the interatomic forces or the spring will be disturbed, and the reaction of that disturbance will be gone to all of the springs, all of the springs, and that's how the elastic body and these forces actually, see, the all other actually will apply a force on this such that, see, suppose this is pulled this way, the other will pull this way, this way, this way, directly or indirectly. So what will be happening, since these atoms are connected to each other by spring like interatomic forces, if one interatomic force is disturbed, then all other interatomic forces will exert a resultant force on this particular changes such that this body regains its original states, like original shape and size. And in general, at the equilibrium situation, the atoms will occupy the equilibrium position or minimum potential energy position, but upon application of the force from external sources will disturb the equilibrium, and then there will be deformation. And if some objects are perfectly plastic, they will not regain their original shape and size. But if some objects are elastic or nearly perfectly elastic, they will regain their original shape and size after removal of the force. Okay, this is about the spring ball model, and that is actually explaining the microscopic nature behind the, or microscopic picture behind the elastic properties of solids. Now we'll learn few definitions which we'll be using throughout this chapter. Stress and strain. There are two things, stress and strain. Stress has dimension of force per unit area, and strain is dimensionless quantity. We'll just learn that. So what is stress? As I discussed in the spring ball model, if a body gets deformed under the action of an external force, then what happens, at each section of the body, of an internal force, an internal force of reaction sets up. If you just go in here again, see when we externally apply certain force, what happens internally also there will be a reaction force generated in that. Okay, if we suppose push this in this way, then internally there will be a force generated, reaction force generated in the opposite way, so that it can oppose the external force which is making the changes of its shapes and size. And this reaction force will be in each section or each part of the body. Okay, so this this reaction force actually enable the object to retain or regain its original shape and size. So what is, and that is actually when we, so this internal force, internal reaction force which is opposing the external force, if we write that force per unit area, if we measure that force per unit area, that is called stress. I'll write the definition. The internal restoring force set up per unit area. Okay, sorry. Internal restoring force, restoring per unit area. So if you apply certain deforming force to an elastic object or in any solid object, there will be a restoring force produced inside the solid internally. Okay, that will tends, which tends per unit area, which tends. So the internal restoring force per unit area which tends to restore the deformation. Okay, so restore the original shape and size. Is called stress. So I'll write in terms of mathematics. So this is restoring, internal restoring force per unit area. So stress is given by the applied force. Actually, this restoring force anyway you cannot measure within, it is within the object itself. So as I said, the restoring force will be exactly equal to the external force. This is restoring force and this is external force. They are equal and opposite. They are exactly equal in magnitude and acts in the opposite direction. So that's why we can measure the stress in the object by applied force, applied force per unit area or area of cross section. So if you write it, you get F by A. Look, this stress has dimension. Stress has dimension of power. Power means CML T to the power minus 2. Okay, this is force, and per unit area means L square, again L to the power minus 2. So it will be together m l to the power minus 1 t to the power minus 2. So this is the dimension of stress, and see this can be written as Newton per meter square. Newton per meter square. It has unit Newton per meter square, or in CGS dyne per centimeter square. Okay, because it is the force per unit area, applied force per unit area. So this is the definition of stress. Now we will go to strain. Okay, so look, before I go to strain, I'll let you know that there are different types of stress. One is called tensile stress or longitudinal stress. So what is this longitudinal stress or tensile stress? It is the restoring force sets up per unit cross-sectional area of a body when the length of the body increases in the direction of deforming force. It is also known as longitudinal. So, okay, so suppose this, see here, differential, okay, different stresses. Okay, so look, this is the tension or tensile stress. This is called tensile stress. Tensile stress. So the restoring forces, suppose you have an object, you have applied forces like this. Okay, if the shape is changing like this way, in this way, and also internal forces or restoring forces are arising in the same direction, like acting in the same direction, then it is called the tensile stress or longitudinal stress. So it is the restoring force. Tensile stress is the restoring force set up per unit cross-sectional area of a body when the length of the body increases in the same direction as the deforming force. Suppose this is the deforming force direction, and direction, okay, direction in the sense along the length, along the length the deforming forces are there. So length also changes in this direction itself. Okay, then look, the tensile stress will be arising in the opposite direction, and that also has a direction of the length only. So when the changes in the sense only the length changes, length changes, and that change happens in the direction of the external force, then that is called the tensile, the stress which is rising in that case inside the material, that is called tensile stress or longitudinal stress. Now compressional stress, you look compression. In this case what happens, the restoring force sets up per unit cross sectional area of a body when its length decreases under the deforming forces. So this tensile stress was actually produced because of the change in the length, that is increase in the length. Now if certain forces are applied to decrease the length of the object, then the restoring force which arises within the object, that is called compressional stress. Now we will see tangential or shearing stress. So this, in this case, you look, if you apply external force equal and opposite on the face of a face, on the face of a certain object, if you apply force equal and opposite to the, like equal and opposite forces are applied on the surfaces surface of the object, then it is called actually a shearing or tangential stress. When deforming force acts tangentially, in other words, if this acts in tangentially, I'll give you a better figure for that. So this is the tangential force, tangential or shearing stress. You can take a match box, open match box, okay? If you take a match box like this and apply certain force, then you look what happens. Apply certain force. See, it will actually get deformed like this. See this. So maybe this will come like this, and this guy will go somewhere like this. Okay, so that means, see, the lower bottom face is remaining at its own position, while the top portion is actually displaced from the bottom face compared to bottom face. If you take your book and just apply certain parallel force on the surface on the top, you look, this is the shape you get. That means you look, the bottom face has, see, earlier the face was like this maybe, okay? So now once you apply this force tangentially on the surface, then see, the top surface has just moved by certain angle, okay, moved by certain angle. So earlier maybe it was there like this. So this is the angle, okay? We'll measure in this case. We'll obviously we'll discuss again this kind of stresses in detail. So this is the change in the change in the angle divided by um, so this is okay. This strain we'll discuss again. So stress is actually denoted by, shearing stress is denoted by tau, okay, and that is A by A. See, the definition of the stress is same for all kind of stresses, whether it is tensile, whether it is shearing, whether it is compressional, etc. So in all cases, stresses are having the same definition, that is force per unit area. Force per unit area. Now we'll learn about another term which is very important, that is called strain. We'll learn about strain now. So what is strain? We know this word is very common for modern society. I'm getting strained. Okay, so strain means, see, according to our science, what is strain? When a deforming forces acts on a body, the body undergoes a change in its shape or size. The ratio of the change in any dimension produced in the body to the original dimension is called the strain. Suppose I say, so I'll write the definition first. When a deforming force acts on a body, deforming force act, acts on a body, the body undergoes a change, undergoes a change in shape and size. Now look, the ratio of the change, the ratio of ratio of the change in any dimension. The ratio of change, suppose it is length or volume or area, whatever. The change, the ratio of change of any dimension in any dimension, rate of change in any dimension produced in the body, produced in the body to the original dimension. I'll write the mathematical formation form for that, then it will be again clear. To the original dimension of the body. Okay, this is called, as I said, it is, suppose strain, if I write the change in the dimension divided by original change, original dimension. Okay, change in dimension divided by the original dimension. Okay, now there are different types of strain, as I have shown you. There are different types of stresses, at the same time there are different types of strain. I'll write first longitudinal or tensile strain. Longitudinal strain, I'll discuss about the strain and then stop the class. Hardly five minutes more. See, the longitudinal strain is, it is defined as the increase in the length unit per unit original length. Or I'll write the mathematical formulation only. Suppose you have an object having length L. Now if you apply a force along the length, and then suppose the length gets changed by this much. Okay, suppose this is delta L. This is the change in the length. So the strain, longitudinal strain, is the change in the length divided by the original length. And see, both are length, dimension of length, so this is a dimensionless quantity. Dimensionless. Okay, less quantity. Stress has dimension F by A, that means dimension of pressure, but strain is dimensionless quantity. So longitudinal strain is the change in the length. It is the ratio of change in the length to the original length of the object. Now volume strain, that is called volumetric strain. So in case of volumetric strain, volumetric strain, so that is change in the volume to the original volume. Okay, that is volumetric change in the, so it is defined as the change in the volume per unit original volume. So when the body is deformed by external force, then this volume changes, and this is actually called dv by, so dv by d, this volumetric change also we'll see sometime. This, okay, So we'll define some other quantities called compressibility and expansibility. Those things we'll define in the next class. And shearing strain. So shearing strain actually, as I said, that it is defined as the angle through which a face originally perpendicular to the fixed face turned on applying tangential force. So okay, so I'll write another shearing strain. Let me shearing strain. See, we have seen that okay, it undergoes a shearing strain. So suppose this was the earlier position. Now it is changed by this much angle. Okay, so this is the angular change upon applying the force. Okay, so this is the angle. So this angle itself is called actually shearing strain. This is theta or tan theta, and this can be obtained by the ratio shearing strain is actually measure of theta angle theta by which it is displaced the upper surface. As I said, shearing stress means lower surface will be remaining at the same position, whereas the upper surface of the object will be little bit displaced. If you take a open matchbox, okay, or if you take a simple book, thick book, and then just press the upper surface tangentially, then you get to see that the lower layer will be remaining at the same position which at which it was earlier, but the upper portion will be getting displaced. So this angular displacement, this theta or tan theta, is given by the relative displacement between the parallel surfaces. It is given by relative displacement between the surface, okay, surface to the perpendicular distance between the parallel surface. Perpendicular distance between the parallel surfaces. Okay, so this shearing strain we'll discuss again in detail tomorrow in the next class, and that day we'll learn one law that is called Hooke's law. I'll just briefly say today what is Hooke's law. So there is something called elastic limit. Elastic limit, as I said, if you keep on applying deforming forces to an object and you apply over and over and over, the elastic object, even though it is elastic, it will loses its ability to regain its original shape and size if you deform the object beyond certain limit. That limit is called elastic limit. Okay, so Hooke law states that the elastic limit within the elastic limit, the stress by strain ratio stress by strain ratio will be a constant. This is Hooke's law. So this is Hooke's law. We'll discuss it again in the next class. So we'll discuss shearing strain and this Hooke's law with elastic limit, etc. in detail in the next class, and along with that we'll learn how to prove Hooke's law and stress strain curve, etc., and also few more modulus modulus of elasticity we'll learn. Okay, so we'll stop it here for today. We'll meet again on Thursday. That day we'll continue to learn about Hooke's law, stress strain curve, and few modulus of elasticity. Okay, so thank you for your patience today. Okay, so bye for today.